Okay, question 2. Biologists from the University of Honduras estimate that outbreaks of intelligent life occur randomly and on average once during the lifetime of every 50 galaxies. Okay, well that looks like a Poisson distribution, doesn't it? Randomly and on average at a fixed constant rate. So part A, show that the probability of intelligent life occurring at least once in the next 200 galaxies is 0.982. Okay, well if we call x the number of times life occurs in 200 galaxies, it's going to follow a Poisson distribution with lambda equals, well, if it's once every 50 galaxies, then I guess once every 200 galaxies is 4 times that, so it's going to be 4 times. And we've got to show that the probability of life is 0.982. So that means we can't use the tables or the calculator, we've got to do it from the formula. And we've got to show that the probability that x is at least once is 0.982. Now the probability of something happening at least once is 1 minus the probability it doesn't happen at all. So now we need to work out the probability that x equals 0. And I'm going to use the Poisson formula for this. So I'm going back to the tables. I'm still on page 25. So I need to go to page 11 because I know that's where the formula for the Poisson distribution is. So page 11, there's the Poisson distribution. Probability that x equals x is e to the minus lambda, lambda is the x over x factorial. So I'm going to just start writing that in. 1 minus the prob is e to the minus lambda, but lambda's 4, lambda to the power of x over x factorial. But of course 4 to the power of 0 is 1 and 0 factorial is 1, so it's just 1 minus e to the 4. 1 minus e to the minus 4. And that should give me the answer I want, so I'm just going to check that. 1 minus e to the negative 4. And indeed it gives us 0.98168, which is 0.982 as required. And just checking the question, stating one necessary assumption. Well, the conditions for the Poisson distribution are independence, constant average rate, randomness, and 1 at a time. And they've given us a constant average rate and randomly, so it's either independence or occurring 1 at a time. And I think they'd accept either, but I think I'm going to go for independence. But I'm going to word it in the context of the question. So the outbreak of life is independent. I'm just going to say between galaxies, which, depending on how galaxies work, may or may not be, but that's not our concern right now. It's just that is an assumption. So that's part A done. So part B, find the probability that intelligent life will occur at least 3 times but no more than 5 times in the next 100 years. So at least 3 times but no more than 5 times. So again, if we use x for our discrete random variable, it doesn't really matter. In 100 years it will be an average of 2, so lambda is 2. And we want the probability that x is at least 3, but no more than 5. Well, that allows 5. And that's, if I just draw my little thing, I find this most helpful. So all of that, but not that. So it's going to be x is less than or equal to 5 minus the probability that x is less than or equal to 2. And I'm going to use the function on the graphics calculator for this. So I need to find the Poisson distribution, so I go to options and I want a stat option, so that's F5, and I want the distribution, so F3. Can't see the Poisson distribution there, so I'm going to go along, and there's the Poisson distribution. And the syntax for the Poisson distribution, the cumulative distribution, which is what I want because it's less than or equal to, is XL, where X is 5 and 2 in our case, and L is the value of lambda 2. So first of all I'm going to do PCD, Poisson cumulative distribution, with 5, X is 5 and lambda is 2. And I get 0.9834. I might just do a bit more, 3, 6, minus, same thing, this time 2, x is 2 and lambda is still 2, and I get 0.66, sorry, 0.6676, and one minus the other is 0.983436 minus 0.676676. And about the only thing that can go wrong there is that I type it in wrong, but seeing as it's all there on the screen I should be able to do that. And I get 0.307 to the standard 3 sig figs. And that's part B. So, part C, galaxies are surveyed in batches of 50, fair enough. So we're back to lambda equals 1. Find the probability that intelligent life will occur at least once in each of the next 3 batches. So now this is a bit more complex. We've got a Poisson distribution. We want to find the probability that x occurs at least once, but then it's got to happen 3 times in a row. So we're going to have to effectively do a probability tree type argument. So if I say that the number that I find is x, again Poisson distribution, parameter 1 this time, and I want the probability that x is greater than or equal to 1, which is 1 minus the probability that x equals 0, which I can get off the calculator again. So 1 minus, now this time it's a probability distribution, not a cumulative distribution, because it's equal to 0. It's the same syntax, XL, so 0 is the x value and 1 is the L value, and we get 0.6321. But we want that to happen 3 times in a row. So the probability that x is greater than or equal to 1 3 times, well, I hope you realise that you have to take that number and raise it to the power 3. The chances of something happening 3 times in a row is that number cubed. So I'm going to do 0.6321 cubed. And again on the calculator, use the answer button for maximum accuracy. Answer to the power 3. And we get 0.2525. So again, 3 significant figures, 0.253. And that is the answer to C. Which just leaves us with D, should say D here really. So what have we got? A random sample of the number of occurrences of intelligent life in 10 batches of 50 galaxies is as follows. So we've got some real data now. Does the Poisson distribution provide a suitable model? So never mind all of our assumptions so far, here's some allegedly real data. Does the Poisson distribution provide a suitable model? Well, we just need to know that in order for the Poisson distribution to be a suitable model, mean must equal variance. So I'm going to go to the menu and I'm going to go to stat mode. And I'm going to put this data in, and actually I've already done it because I've already done this question once before, so I'll just make sure I've got that data in while you get your data in. So we get 0, 1, 2, 1, 3, 2, 0, 1, 1, 0. So there's my data and I'm just going to calculate the mean and variance. So calculate one variable data. Bingo. Now I don't get mean, I don't get variance, I get standard deviation, so I'm going to have to square one of those values, so let's get ready to do that. So first things first, mean equals 1.1 and the variance, now I'm going to use a sample variance because it is a sample, is that value 0.99442892 squared, and you've got to use the right value. They will penalise you if you use the population variance. So back to calculator mode, 0.99442892 squared, and we get 0.9889. So I think I'll just call that 989. And so we look at the mean 1.1, we look at the variance 0.989. Are they pretty close? Well, yes they are. So we say since mean is approximately equal to variance, the Poisson may be a suitable model. This test doesn't guarantee it is. If mean isn't equal to variance, then Poisson definitely isn't, but them being the same doesn't guarantee it, so that's why we say may be a suitable model. But that's all they're asking. And that's it. Now let's just see where the marks come in this question. Part A is 2 marks, 1 for subbing the numbers into the formula and 1 for showing that you get the right answer. Part B is 3 marks. We get 1 mark for setting up the calculation, 1 mark for getting the right values, and 1 mark for the correct answer. So there are 3 marks here. Part C, again 3 marks. We get 1 mark for getting the value of it happening once, 1 mark for cubing it, and 1 mark for getting the right answer. So 3 marks. And the last part is just 2 marks. 1 for getting the right values for the mean and variance here, and 1 mark for this statement. And we have to have both parts of that statement. We have to say, since the mean equals the variance, the Poisson may be a suitable model. And that's the end of that question.